If we know that a sample is normally distributed, then we can automatically conclude some properties about that distribution. The 68, 95, 99.7 rule will apply to all of our normal distributions. Here's how the rule is stated. In a normal distribution, all of the following are true. 68% of the data lies within one standard deviation of the mean. 95% of the data, that's almost all the data, lies within 2 standard deviations of the mean. And 99.7% of the data lies within 3 standard deviations of the mean. So to understand what these rules are expressing, it really helps to visualize this on a graph. Suppose that we have a data set that we organize from smallest to largest on a number line. In a normal distribution, the data is centered about the mean, and we measure distances above and below that mean in terms of the standard deviation. So one standard deviation above the mean, we could say, is x bar plus s. 2 standard deviations above the mean is x bar plus 2s, and 3 standard deviations above the mean is the mean plus 3 times the standard deviation. And this is true on both sides of the mean. If we're working above the mean, we add the standard deviation. If we're working below the mean, we subtract a multiple of the standard deviation. Make sure that's a minus in there. Okay, and then our normal distribution again follows the bell curve, or the shape of a bell. Don't forget that on the vertical axis, we are measuring frequency, or how often that particular data point occurs. So our data is organized smallest to largest on the horizontal axis. The frequency, or how often that data point occurs, is measured on the vertical axis. So because we have this hump here in the middle of the bell curve, that means most of the data tends toward the center around the mean. In fact, that mean is going to divide our distribution in half. On the upper side of that midline, we have 50% of the data, and on the lower half, we have another 50% of the data. So it divides it right into, let me move this label down a little bit so you can read it. We're going to have lots of information to display on this one graph. So half of the data, 50%, is above the mean, and half of the data is below the mean. Now on this graph, we're going to interpret these rules. It says 68% of the data lies within one standard deviation of the mean. So that's one standard deviation above the mean and one standard deviation below the mean. So if I look at the number of data points between x plus a standard deviation and x bar minus a standard deviation, I would see that represents 68% of the data. So if we consider this bell curve to represent SAT scores, we would say 68% of the people who take the SAT test score within one standard deviation of the mean. That means they could be one standard deviation above or below the mean. Similarly, 95% of the data lies within 2 standard deviations of the mean. That is almost all the data. And finally, 99.7% of the data lies within 3 standard deviations of the mean. That's, again, almost all the data. Missed my mark over here. Try that again. So the standard distribution is symmetric about the mean. Again, half the data is above the mean, half the data is below the mean. 68% falls within 1 standard deviation of the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. All normal distributions are going to exhibit this property. Now, even though all normal distributions have this property, all normal distributions are not exactly the same. Some normal distributions may have a smaller standard deviation. What that means is you've got your mean in the middle and you've got a small standard deviation, so your data is closely packed around the mean there in the center. Or you may have a smoother, more gradual looking bell curve. It's still a normal distribution and it still exhibits the 68, 95, 99.7 property, but the standard deviation is larger, so your data is more dispersed around that mean, giving you a smoother, flatter bell curve. regardless of the size of the standard deviation, this is a small standard deviation, and this one is a larger standard deviation, at least relative to each other, they still follow the same properties of the bell curve. Let's keep these in mind and keep that diagram handy so that you can refer to it and see if we can answer the example questions. Let's suppose a specific car model is sold for different prices in different locations. The price of a car is normally distributed with a mean of $17,500 and a standard deviation of $500. Before we answer this question, let's make sure we have a good understanding of what this bell curve looks like. So I'm going to use the space over here. Let's suppose that we organize the prices of cars sold from smallest to largest on this number line. Right smack dab in the middle, we're going to have our mean, or the average, of $17,500. Now, the standard deviation is $500. That's the unit that I'm going to use to measure distances above and below the mean. So one standard deviation above the mean, that's $500 above that one, we'd have a price of $18,000. Two standard deviations above the mean, we'd have $18,500. And three standard deviations above the mean, we'd have a price of $19,000. Going below the mean, $500 below the mean, we'd have $17,000. Two standard deviations below, we'd have $16,500. And three standard deviations, $16,000. Again, right here in the middle is our mean, X bar. So we'll say the bell curve takes a shape something like this, remembering that the number of cars, or the frequency, is measured on the vertical axis. Number of cars sold. Having this diagram will certainly be helpful. I'm going to redo this so it's centered a little better. Right above the mean. Having this as a guide will be really helpful in visualizing these questions. And don't forget that that mean divides that distribution right in two. The first question is, what percent of customers pay between $16,500 and $18,500? So $16,500 and $18,500. If I look at this, notice this is two standard deviations above the mean and two standard deviations below the mean. So we need to know what percent of the customers are within two standard deviations above the mean. So this is two standard deviations below. This is two standard deviations above. If we come back up here to our rule that we identified, we can see that 95% of the data lies within two standard deviations of the mean. That means 95% of customers will pay between $16,500 and $18,500 for a specific car model. Now, I love talking to you about this because we can revert to Chapter 8, and I know that you could calculate the car payment for a $16,500 loan or an $18,500 loan, right? There'd be a big difference, of course, between those two. Okay, next question. What percent of customers pay more than $17,500? More than $17,000. Now remember, $17,500 is the mean. So we're looking at what percent of customers are above the mean. The mean divides the distribution right in two, and we know that there is 50% above the mean and 50% below the mean. So half of our customers are going to pay higher than that average price of $17,500. We know this because the price of the car is normally distributed. If the distribution is not normal, it follows another shape, then we cannot make that conclusion. Let's try the next question. What percent of customers pay more than $18,500? Well, if we look at our diagram, $18,500 is two standard deviations above the mean. And we know from our first example, 95% of the data is within two standard deviations of the mean. So if I look at this little box, we've got 95% of the data between 16,500 and 18,500. We're trying to figure out what percent of customers pay more than 18,500. Now don't forget that the normal distribution is symmetric about the mean. So if I look at this green area, the 95% that lies within 2 standard deviations above the mean, I know half of that 95% is above the mean and half of that 95% is below the mean. So if I take 95% and divide it by 2, I end up with 47.5%. So I know 47.5% is 2 standard deviations above the mean, and 47.5% is 2 standard deviations below the mean. Now, if we know that from this line to this line, we have 47.5% of the data. Now, I wrote that down there in the green box. I'm just writing it up here next to this 50%. To help you figure out, well, if we know how much is between the mean and this vertical blue line, right, 47.5 between those two lines, and we know that there's 50% completely above the mean, then we can figure out how much is above that 18,500 mark. If we take 50% minus 47.5, we would find 2.5%. So again, the 47.5 plus the 2.5 gives us the 50%. Where did that 47.5 come from? We're taking this interval from the rule and simply dividing it in two, splitting it about the mean. So 2.5% of customers are going to pay more than $18,500. Let's try one last question. What percent of customers pay less than $17,000? Well, let's look at $17,000 on our graph. Notice $17,000 is 1 standard deviation below the mean. So I'm going to look at the first part of our rule. Remember back here, 68% of the data lies within 1 standard deviation of the mean. So on our example, we know that 68% of the data is between those 2 standard deviations. I'm just going to shade it in here. And we know that this is divided in 2 by the mean, right? So of that 68%, 34% is above the mean, and 34% is below the mean, just using symmetry here. So looking at the left side of our normal distribution, we know that there's 34% of the data between the mean and 1 standard deviation. And we know that on the entire left side of the mean, we have 50% of our data. So if we have figured out that 34% of the data is between the mean and 17,000, then we could take 50 and subtract 34% to figure out how much is here. 50 minus 34 gives us 16%. So again, if I take the 16% plus the 34%, that gives me the total 50%. Where did the 34% come from? We were taking our rule that says 68% of the data lies within 1 standard deviation of the mean, and we divided that into half above and half below. So 16% of the data, 16% of customers would pay less than $17,000. So the key to working a problem like this is simply understanding that if it is a normal distribution, then automatically we get these 3 conclusions. In addition to those conclusions, we can use the fact that the normal distribution is symmetric to make these predictions about where specific data points occur. So take some practice, draw the pictures certainly help, and use that symmetry to solve those problems.